Wonderful. Thank you very much, Ilka, for chairing the session and introduction. Thanks also to the park team, Justina, Katja, Ludger, Andrea, everybody who there. You're always doing a very nice job, and I would like really to appreciate that and also mention it here. I've decided for the 2 days talk to again switch on a topic that has not so much been really discussed here, at least not on the NSFE, I think. And this is really going for optical really means by using scanning force microscopy. So no worries, we will see scanning force microscopy images, but we couple that to really radiation. And to cope that even more, we go for infrared and terahertz because we can learn a lot on phonons and interactions in solids by using that. And in fact, we have the power then combining the scanning force microscope down to really very small length scales. Now, this topic basically complements earlier talks, and if I may just quote, in 2018, I was already talking about chemical sensitivity of STMs or SPMs in general, STM and scanning force, which ended up in Kelvin, in fact, and we had also to digest all that with some kind of really good liquor. Otherwise, it was not really digestible, at least on my talk. So you see the liquor here. If we just bridge over to 2019, it's a very nice conference organized by one of the speakers of today, Tobias. The topic was really to digest magnetic force microscopy with a good red Italian wine. 2020, we had the first virtual conference where I was rather speaking about CAFM measurements of domain wall currents, as you can nicely see here in this picture. And this was really, unfortunately, only virtually, but also physically in my home office, as you see here, really poured into with a really good Trinity package of whiskeys from Teeling. And last year, we had good German beer to really digest the more stuff actually that I was presenting on the sample stream. So I definitely know what to talk about today, because as I said, I want to talk about near-field optics. And you see nicely, basically, we take in a scanning force microscope tip, illuminate that tip, and want to really learn something about our sample here. But what I don't know, that's the question mark for, is what kind of beverage Justina will serve for this year's the NSFE 2022, so to say, lectures. I presume it's not going to be, as I'm showing here, a blonde couple of
I was sure someone will complain about that, and there you go. I promise we'll make it up for you next year.
Fantastic.
Double shot for you.
So we keep the question mark, and then we can cheer later on that. So let's open the curtain basically to talk about near-field optics. And as everybody knows, if you take a far-field optical measurement, if you take a far field, which means basically you just take a wave that is propagating and you want to basically focus that, we cannot beat the diffraction limit, which means for terahertz or infrared ranges, we end up with a spot size of 150 microns. So this is really huge. This is nothing you can gain on. So that's why we have to go now for near-field optical measurements, and historically apertures, as you can nicely see here with this punched card hole of a 1 micron diameter, could do the job. This is nothing else than the famous camera obscura. You look through a tiny, tiny hole and provide, so to say, a spatial, a K-space filter, which is very nice. So for instance, to increase the resolution. But we are much more severe today actually to say, well, why not to use so-called Babinet principle by using a scanning tunneling microscope tip on the left side, or as I will really introduce here, a scanning force microscopy tip, because the AFM is much more versatile in addressing questions on any material of your choice, not only, let's say, conductive materials as the STM here. So what I will show to you is now how to operate that. What is the essence? Why is this very important? What can we learn? And in fact, we see we can have material contrast. We can go for nanospectroscopy. We can merely map out local electric fields and local excitations. So again, the physics behind that is that we take an illumination. So we come here from the top right, either visible, infrared, or terahertz range, doesn't really matter. And what you physically do is you take your tip of a scanning force microscope. This is an ordinary tip, everything that you can buy on the market. You induce a dipole. This is my red arrow here, which is actually an induced dipole into a tip. So the tip acts like an antenna. This dipole then finally, this induced dipole, induces a sample dipole. That's the green arrow here in my sample, which is a molecule for this cartoon here. And in fact, these two dipoles, the red and the green, they start interacting. It's dipole-dipole interaction. It's an induced dipole-dipole interaction, depending naturally on the distance, depending on the strengths of these dipoles, depending on the wavelengths and so on. But in general, the two of them are then scattered back to my detector in the far field. So the nice thing is really that both illumination as well as readout is in the far field. I take an ordinary AFM mimic, most preferably non-contact, but you can also go for contact, doesn't really matter. We get a confined near field, and we can probe near surface properties. I will come to this point in my lecture here, simply because we are also looking a little bit undercover. So we can really probe into the bulk, into beyond the surface of the system. That is interesting, for instance, for layered materials, to also probe something on the internal interfaces. We can vary the wavelengths simply because the resolution that we get with this kind of mimic is not given by now the whole of your punch card or the illumination wavelengths, but it's really given only by the tip diameter. So you take care basically not to ruin your tip, your nice ruin and very expensive tips. In that sense, really don't crash it on the surface. But nicely enough, we can operate that mode also together with anything that you like to know. So that means we can go for topographic imaging, we can use KPFM simultaneously, we can use MFM simultaneously, and so on. You can use CAFM, and hence probe quite a bunch of really properties like elastic scattering properties. So you go in and out at the same wavelengths, or inelastic properties like Raman, Stokes, anti-Stokes. You can go for absorption and so on. So if I digest that in a mathematical formula, what we need to know basically is, what is my tip polarizability? You see that here. The polarizability means how strong that dipole in the tip is, because we shine in from the top left, in this case here with some electric fields. And then the response function beta, which is exactly how much is my sample responding. The epsilon s is the sample dielectric constant, as you can see here. And this can be quite versatile, can be quite complicated, because like shown here on the bottom, it can be layered structures, which means a combination of different layers. If you stack HBN on indium selenide or so, as we have seen this morning in one of the lectures, or if you have something like domains staggered to the right and to the left, and so on. And moreover, if you get anisotropic properties, which means X, Y, and Z axis of a Cartesian system is not the same, then this whole thing becomes quite complex. So we take a lot of advantage now to really tune the resonance of this whole overall polarizability to the beta function, which is the sample response function. That means we want to adjust the omega by changing the wavelengths in order to get the sample responding, because then we want to listen. We want to listen to the phonons of the sample rather than actually listen to the tip, what it does. So this is actually an argument generally. So the costly part in this is actually to find now really generation of light, not in the visible range as we do see here for plasmons, which is typically on the order of about really nanometers or hundreds of nanometers, but going down in wavelengths to a couple of 100 microns even, or let's say a few microns only, like 354, which is the fingerprint region for molecules. But we need these kind of sources that can really do the job there. And only then are we really able to really differentiate between electronic properties on the one side and vibrational properties or rotational properties of the whole system. But that's the whole scale. So you can start at visible light and then really go down and explore the whole thing. What you also see from this cartoon here is one thing, that my epsilon function here, it's really written down, is a complex function having a real part, epsilon prime, and an imaginary part, epsilon 2 prime. Everybody knows that the epsilon 2 prime part, these are the losses, goes hand in hand with what we call absorption. But that's exactly what we have to do. We want to explore this epsilon function now in the near field by coupling exactly this mimic. So we were lucky, and we are still lucky actually in Dresden, that we have nearby at the Helmholtz Center a laser system, which is called a free electron laser. As you can nicely see here, we have an electron bunch. So these are really electrons that come out. So same thing like with your electron microscope. And then enter into a so-called wiggler, which is arranged between north and south pole magnets. So the beam goes like a fish goes and swims through the magnets and wiggling around front, back, front, back, front, back. And you see the cartoon enlarged here. At every turnover, it radiates a so-called Bremsstrahlung. This is radiation, which is very monochromatic. And you can collect that in a resonator, similar, as you know, from a laser, and hence just digest this kind of different wavelengths. And we have two wavelength sets, actually, in our case, which is one called Felber and Telbe. And you can see the cartoon or the numbers here. One goes from 4 to 250 microns, covers also the fingerprint region for every organic material, while the other one goes even down to below, or let's say above 1 millimeter. So you see nicely we bridge the famous terahertz gap. So this is now very important. This wavelength tuning is the holy grail in our setup because we can now address for any kind of quasi-particle excitation, plasmons, phonons, magnons, spinons, you name it, or any coupled polariton. We can couple a photon with a plasmon, we can couple a phonon with a plasmon, and so on. These are all quasi-particles. Now you want to do that also not only at room temperature, but we have invested a lot in the recent years to do that also at lower temperatures. That's why we have a lot of MMIC. So to give you a couple of examples, what is the holy grail is naturally this epsilon function. I have really replotted this epsilon right here. It's, as we see, complex. It's a tensor function. And I would like to really walk through with you into 4 different examples shown here, starting with a simple one that everybody knows, which is gold. Now, in the community, you call this epsilon function not dielectric function, like people do, for instance, in engineering sciences, but you call it optical conductivity. They mean the same thing. It's the epsilon function, which is complex and real. Now, for gold, as we see, this blue curve, the real curve, it goes up, down from very negative epsilon values. And if you would follow up here to the right, it would cross over the 0 line at about 4 to 5 electron volts. That's a famous plasma frequency. That's exactly when you go to churches and you see these fantastic colors on your windows. It's really the blooming nice colors actually giving. So that's exactly the famous plasma resonances. The imaginary part of this gold, so to say, the gold here, the red part, simply goes down with a function of 1 over omega power 3, nothing special. And in fact, this curve of gold never has any other resonances. It's finished like this. The only crossover is this plasma frequency. That's for all metals. That's good. Now look on silicon, another famous material. Oh, wow. The real part, basically blue, is really flat here. You see typically at M.7, which is my epsilon, typically flat over the whole range, not too many resonances. And we get an absorption here, typically at about 70, 75 millielectron volts, simply to see, there's a single resonance for pure silicon. What about silicon dioxide? Bottom left, C panel here. Oh, wow, we have many more wiggles. There is really more history and more really structure in there. So we have to really choose the right laser to do that. And in order to do so, to mark it for you, I've just marked the CO2 laser, which is 10 micrometers wavelengths. If you take another modern type multiferroid material, gallium vanadium sulfide at room temperature, these are the resonances you're going to find. So in fact, what that means is we have to adjust all these resonances exactly to what you want to measure, what you want to see from your sample. And that's why I've chosen for the rest of this lecture here to show you 4 examples. I will start with a semiconducting core shell nanowire, then go for buried nanostructure if you want to look on the cover, then switch to really 2D materials as introduced this morning already, which is alpha molybdenum trioxide, which is a nanosotropic system, and then finally ending up with superlensing and metamaterials, which brings us a little bit into the history or into the story of Harry Potter. So let's see here. We start simple with nanowires, one-dimensional structures. You see them growing on the surface like silicon. They go up like pillets shown here. It's like a grass that is really growing. And if you look inside, there's a core, typically of 25 nanometer diameter, that has been really grown over concentrically. And you see basically the whole thing goes up to about a 200 nanometer circumference, let's say widths in total diameter. Now, this structure contains then electronic properties that are both metallic on the one side, because we have free charge carriers. The charge density typically is on the order of about 10 to 12 per centimeter square. But on the other side, it's also semiconducting or quasi-insulating. So that was exactly the property we wanted to really probe with our now scanning force microscope. You see here the cantilever being approaching such a nanowire and then illuminating here from the left with different light. And we have chosen to do that with two different laser sources. Before we do this in the experiment, let me go and just digest again what the theory would expect. So illuminating that tip, inducing a dipole, couple that to the nanowire would mean that on the one side, we could have on the right side here, just to the right here, more electronic properties. We call these plasmonic properties. You see nicely omega PL or omega P. This is the plasma resonance. Or in the middle term, we could have more Lorentz type oscillation, simply because we have more dielectric or more insulating properties. That means we have the TO, transverse optical oscillation mode of this structure. So since we don't know what is really true, we said, okay, let's come up with a formula like, as you see here, which is everything. So this is the fitting curve to our data in the end, which is actually a Drude on the back here and a Lorentz model. That's why it's called Drude-Lorentz. Now, the nice thing, and that's exactly the sophisticated goal here, is that from a good fitting, we could deduce many, many things. We need to fit the plasma frequency, the losses, and then directly deduce the number density of electrons in this nanowire. We can deduce the effective mass of the system, which means the electron that is really vibrating here. And moreover, we can also deduce the effective mobility. And everything is really local. It's contact-free because you don't need to put on a wire in order to do so, and it's non-invasive. That's really a nice thing. So what Danny did is actually saying, okay, let's do the experiment with two lasers, CO2 and then FEL. And the difference between the two is one thing, that the CO2 laser is a continuous wave. It's always on. We never stop that laser. It's shiny. While the FEL is a pulsed source at 30 megahertz, which means we get a much higher peak power. That's actually shown here in the imaging on the top bottom right, than actually for the CO2 laser, which also means in the end that the numbers that we get out from this kind of measurement using exactly this mimic is different. The plasma frequency.
3 minutes left.
We feel? How much?
3.
Okay, cool. So the plasma frequency is much higher. Here you see basically the damping is actually much lower, and so on. So you can deduce all these values here fantastically. Let me switch to the second example, which is buried structures. In a buried structure, we want to look under the surface, and we have prepared a sample, which is 100 nanometer below the surface, a boron implanted system. We apply exactly the same technique, and by scanning through the old sets of really wavelengths, you can really deduce exactly the number density N of all these electrons that you have there. And in fact, what we come up by doing the fitting here is a fantastic experimental matching for 3.7 rather than 4 that the theory expects. So this second example shows you we're not only looking at systems at the surface, but we also can look to systems below the surface. Third example, we come to 2D materials. And this is actually a 2D material, which is molybdenum trioxide, which is a layered structure. You see basically here this cuboidal structure, and every layer 1, 2, 3 is a molybdenum trioxide layer. They're stacked, so to say, along the B-axis. And the B-axis, if we go there, is the 0, 1, 0 axis. So to make this clear to you, we have 3 axes, X, Y, Z, which are all different. And in fact, all the 3 axes are different in their epsilon. You see this here, red, epsilon Y. You see a green, epsilon Z, epsilon X. And this means one epsilon always can turn negative, like shown here for the epsilon Y. Here it's the greenish area, and here's the bluish area. Or in other words, our anisotropy of phonons shows up that some of these components in my tensor becomes negative, others are positive, which gives us a possibility to image these phonons along different directions. For instance, as you see here, at 9.22, All these phonons are propagating along the y-axis. These are the wiggles that you see here in the real space image. While if you change to 11.17, all these wiggles are to the right, which is bluish here. So that means we can differentiate between different type of phonons, between even different type of couplings by changing the whole wavelengths. And this is really the take-home message from this part, we can really map out the full dispersion relation. This is the energy scale up, while on the x-axis you see the momentum decay. And that's exactly the holy grail for everybody that is really doing solid-state physics. We want to have E of k images for different thickness of flakes here. Let me come to the last part, which is the Harry Potter stuff, which means simply that having said that real part of epsilon that could become negative now has the advantage to construct metamaterials, materials which have a negative epsilon, which means that optically the refractive index, as we see it on the left side here, which is positive here, should also change to negative refractive indices, which give us the reason to really go for physics, which is totally beyond what we can imagine at the moment. And to get you on the same page, we want to focus a point, illumination, to a point which is not possible in the far field, simply because of this famous diffraction limit, as you know from the Rayleigh formula. You have a limited size of your image. Now, what it means if we take this kind of metamaterial, which is now the middle part here, my metamaterial, we would be basically coat that, having a negative refraction. We don't go up like the greenish arrow here, but we go rather down, cross over, and then at this second interface come back to really make a point-to-point projection. And that this is not really illusion or something that has been really thought out by theoreticians, like the Pender paper cited here, is shown here, that this is now a SNOM image where Susanne Kehr and my group has taken the cantilever, scanned it through the spot here, making a 3-layer approach, which means having 3 layers of a simple perovskite material, which is PCT, BFO, and STO. You can work it out. Any kind of these layers can do the job. You have to find 2 solutions, as shown here, where the real part of one material is exactly opposite to the real part of the other one. And then you get exactly this kind of metamaterial superfocusing, which has tons of applications. Here again, I show this very nice super spot. And with this, let me finish to my summary. What I wanted to show to you is actually that near-field optics has the power to combine scanning force microscopy to probe also a versatility of different, let's say, quasi-particles, either at the visible or terahertz range, but at a resolution which is ways beyond what you have in the far field. And what I showed with the 4 examples is actually that we can really quantify, we can get numbers in a non-destructive way to effective number densities of electrons, mobilities, effective masses, so to say, but also to obtain subsurface information on these polaritons. Thank you very much for your attention.